Hi, welcome to my presentation. I'm Jaewon from Korea University, researching at MRV Lab. Today I present my paper, PRESTO, which is published at NeurIPS 2025. Before we talk about PRESTO, I will briefly introduce the instruction optimization. Instruction optimization aims to find optimal instruction that guide black box large language model to generate the correct response for a given input prompt. However, optimizing the instruction is very challenging since the instruction is a high-dimensional and discrete sequence. To address this problem, recent methods employed white box large language models to generate candidate instructions from optimized soft prompts. Specifically, we search the optimal soft prompt via black box optimization algorithm to generate the optimal instruction. Black box optimization algorithm consists of two steps. First, we train the score predictor by MLC loss. And second, using this trained score predictor, we select the next query, which is soft prompt. However, white box large language models often map different soft prompts to the same instruction, leading to redundant queries. The set of soft prompts that generate the same instruction forms the preimage of that instruction. We measure the preimage statistics across the diverse white box large language models. As shown in the given figure, given 10,000 distinct soft prompts, the white box large language models generate a much smaller number of unique instructions. While previous studies have treated this many-to-one mapping as a structure that hinders the efficient optimization, we reinterpret this as a valuable structure that accelerates the efficient optimization. Now, I provide our first method, score sharing. Once some instruction is evaluated by a black box large language model, we share the score to all other soft prompts in the same preimages of evaluated instruction. As shown in the right figure, score sharing method effectively enlarges the amount of scored data without additional cost to the black box large language model. Next, our second method is preimage-based initialization. Our goal is to select initial preimages that maximally cover the search space. Let's assume we have soft prompts from 3 preimages and select 2 preimages to maximally cover the search space. Among 3 choices, the middle one maximally covers the search space, so we choose the preimages 2 and 3 as an initialization data. Lastly, we propose score consistency regularization. While previous method leveraged MSE loss to train the soft score predictor, our score consistency regularization term ensures the consistent prediction within the same preimage. Here is our main table. It shows that our PRESTO achieves softer performance compared to diverse strong instruction optimization algorithms. Here we analyze the effect of score sharing method. We measure the number of scored data under the same budget after optimization process end. In this figure, process yields 14 times more scored data than all previous methods. Next, we visualize the initial data distribution. In this figure, we plot the entire candidate data as gray dots and the selected initial data as red dots. Compared to previous works, PRESTO effectively selects the initial data that densely and evenly cover the search space. Lastly, we analyze the effect of score consistency regularization. We measure the RMSE of the score predictor after applying our proposed method. Compared to the vanilla model, which is trained only by MSE loss, applying our method reduced the RMSE by 43.6%. For access to main paper our PRESTO, we provide QR codes. Thank you for listening.